Hi, Amri.
Hi, Vijay. Hi, Sudhir.
Hi.
Good morning, Professor
Good
Satyadev.
morning, Vijay. Good morning. Good morning. Good morning, Vijayji.
Good morning.
I am Satyadev.
Yes.
We have 1 minute to 9. So, do we start at 9?
Yeah, maybe. Just a second. Where is Piyushanji? Is he here? Professor Piyushan?
Good morning, sir.
Good morning.
Respected dignitaries.
Hello?
Sir, shall we start, sir?
Yeah, is it Gajanan?
Sir, this is Dr. Suryakant Sapkal from IMG University.
Acha, okay.
Colleague of Gajanan.
Yeah, maybe it is time now. Yeah, maybe you can start. Yes, perhaps.
Okay,
Yes.
sir. Okay.
Yes, time we can start now.
Yes.
9 o'clock we can start.
Oh,
Yes.
you are here, Piyushanji?
Yeah, I'm here.
Okay. So we can start it. Yes.
Respected dignitaries, all the guests, today's presenter, chairperson, and all the participants. A very pleasant morning to all of you. On behalf of EMGM University and IMS, I, Dr. Suryakant Sapkal, I welcome you all for the 87th annual conference of the Indian Mathematical Society and International Meet, third day session, morning session, that is 32nd V. Ramaswamy Aiyer Memorial Award Lecture. For this lecture, we have with us a renowned speaker, Professor Vijay Kodiyalam, IMSc Chennai. And for this session, I would like to request Professor Sudhir R. Ghorpade from IIT Bombay and past president of IMS. I request Professor Sudhir R. Ghorpade sir to accept a chair of this session. Over to you, sir.
Thank you. So, it is my pleasure and privilege to chair this session where my good friend and a very accomplished mathematician, Professor Vijay Kodiyalam, will deliver the 32nd V. Ramaswamy Aiyer Memorial Award Lecture. Most of you know that Professor Ramaswamy Aiyer was one of the founders of the Indian Mathematical Society, and we are very happy that we have Kodiyalam to talk. Know about him. I'll just say very quickly, he got his BTech from actually in science from IIT Madras, and then to Purdue University in US, where he did his master's and PhD. For some time, we were students together. Then he worked in the US at the University of Kansas for some year, and moved to the Institute of Mathematical Sciences in Chennai, where he has been for many years. He specializes in actually many areas of mathematics. He started in commutative algebra and moved to subfactors and sister algebras. He has been awarded the Birla Science Prize. He's a fellow of the Indian Academy of Sciences and the National Academy of Sciences. And today he will speak to us on Ramanujan graphs. Vijay, please.
Yeah. Can I begin?
Yes, please. Yes.
Thank you, Sudhir, for this introduction. And let me begin by thanking the organizers for inviting me for this Ramaswamy Aiyer Memorial Award Lecture. So let me first try to share screen. So is the screen visible, the whiteboard?
Yes, sir. Yes, sir.
Yes,
Yeah.
it is visible.
Okay. Yeah. So the picture on the left is of V. Ramaswamy Aiyer. As Sudhir said, he was one of the founders of the IMS. And although he was sometimes called professor, he was not an academic. He was a civil servant and at one point a deputy collector. And he not only founded the IMS, he also served it in various capacities. In the early 1900s, Ramanujan applied to him for a job. And according to Kanigal's book, The Man Who Knew Infinity, Kanigal says that after going through Ramanujan's notebooks, Ramaswamy Aiyer decided that he had, and I quote, no mind to smother his genius by an appointment in the lowest rungs of the revenue department. And then he sent him off to Madras with recommendations to his mathematical friends. So that brings me to the topic of my talk today. So I'm going to speak on, let me try to write and see if it's okay. On Ramanujan graphs. So is what I'm writing visible?
Yes, sir.
Yes.
Yes, sir. It is visible, sir.
Okay, fine. So I mean, I really prefer board talks. So I'm going to make do with this iPad and see how it works. Okay. So Ramanujan graphs are actually somewhat removed from my area of research, but I thought I'll talk about it since it's a fairly recent piece of very beautiful mathematics, and it has led to the solution of more than one long-standing open problems. So the work that I'm going to talk about has been done by 3 people. So here is the So everything I'm going to talk about is contained in this paper called Interlacing Families 1, Bipartite Ramanujan Graphs of All Degrees, which appears in the Annals in 2015. And this is the work of Adam Marcus, Daniel Spielman, and Nikhil Srivastava. So my goal in this talk is basically going to be to try and motivate and explain all the terms used in the title. And not only that, it's such a beautifully written paper that it will be possible for me to give almost proofs of lots of things. I may not be able to do the entire thing, of course, but certainly it's going to be possible to give proofs of lots of things, and I'll try to do most of it as much as I can. So I'll explain what Ramanujan graphs are, why they are studied, what are interlacing families, that's the thing that occurs in the title, interlacing families of polynomials, and how they lead to a beautiful construction of Ramanujan graphs of certain families, actually, of Ramanujan graphs. So here is the rough plan of my talk. So this talk is going to be really elementary for the most part, except maybe at the very end. So I'll begin with some elementary graph theory, and then move on to spectral graph theory. These are needed in order to even define the term Ramanujan graph. So third, I'll speak about expanders and Ramanujan graphs. I'll define these terms. Then we will continue to how these graphs are constructed. The first process in this construction is a certain doubling process for graph called two lifts. So I'll say something about two lifts of graphs and their properties. These two lifts of graphs are related to something called the matching polynomial of a graph. There are various polynomials associated to graphs, like the chromatic polynomial or the characteristic polynomial of its incidence matrix, various algebraic invariants to graphs, polynomial invariants, and one of them is the matching polynomial. So we'll say something about the matching polynomial of a graph. Then after this, we'll actually come to the main new idea in this thing, which is the idea of interlacing families. Interlacing families of polynomials. And in the last part of the talk, I'll do some of the technical part. Not very much, probably. I'll do a little bit of it. So this is the basic plan. So let me begin with section 1 on elementary graph theory. So this talk, as I said, will be almost completely elementary. Even a first year BSc student should be able to follow most of what I'm going to say. So with the result, it may be a little boring to the experts. So I apologize for that, but I think it's probably better to do it this way. Okay, so to begin with, so we take a graph G, which we consider as a set of vertices and a set of edges. An edge E is a subset of the two element subsets of vertices. So E is a subset of this thing. And so that means in particular, our graphs are unoriented first. This is just to set up basic terminology. Graphs are unoriented. They are simple. That means no multiple edges between vertices. and no loops at vertices. So unoriented simple graphs, and for the most part we will deal only with finite graphs, and almost always they will be also connected, even if I forget to mention this sometimes. So we are going to be dealing with connected, finite, unoriented simple graphs. This is the basic setting. So here is one interesting example of such a graph. And this is an example of such a graph. This is the so-called Peterson graph. So it's a named graph, Peterson graph. As you can see, it has 10 vertices and 15 edges. And one important feature of this graph, which will be important for us, is that this is an example of a three-regular graph. That is, at every vertex, there are 3 edges that come to that vertex. So all vertices are of degree 3, and that's the definition of a three-regular graph. We will mostly be interested in d-regular graphs for arbitrary d. So we want d-regular graphs for arbitrary d. So here is an example of a general d-regular graph for any d, and that is the complete graph. So if you take the complete graph, so it's a rather large picture. Let me try to reduce it a bit. Okay, I'm not able to do it. Okay, anyway, so this is the complete graph K5. So K5, complete graph on 5 vertices. So this is a 4-regular graph. In general, KD plus 1, the complete graph on D plus 1 vertices is a D-regular graph. At every vertex, there will be D edges which join all the other vertices of the graph. So this is one example of a complete graph. So next, let's move on to what we want. So if the title says bipartite graphs, so the next thing I want to discuss is bipartite graphs. So a bipartite graph is something that looks like this. Here's an example. So a bipartite graph is a graph of this form. So the vertices are partitioned into 2 sets. And so in this case, one set is red and other set is blue, and no edges between vertices of the same color. So this defines what is a bipartite graph. Another characterization of bipartite graphs is so characterized as graphs not having any odd cycles. So any cycle in this graph, that is a sequence of vertices which goes around the graph and ends up at the same point, is necessarily of even length. That's clear because each time you make one move, you have an edge which goes from either red to blue or blue to red. So if you want to end up, you need to make an even number of moves. The converse is also true. If you do not have any odd cycles, then it is possible to partition the vertices into 2, such that there are no edges between vertices of the same part of that partition. So we are going to be interested in bipartite graph. This is the graph K33. So 3 vertices on either side. Similarly, you have KDD. So that will be a bipartite graph with which is a d-regular bipartite graph. Okay, so this is as much as we will need of basic graph theory. So now let's move to second part, which is spectral graph theory. So in spectral graph theory, the main notion is that of the spectrum of a graph. In fact, the very notion of a Ramanujan graph is spectral in nature, so it depends on the spectrum of a graph. And so what is the spectrum? So associated to a graph is adjacency matrix, which is a square matrix indexed by vertices. Both the rows and columns are indexed by vertices, and this entry is 1 if VW is an edge and 0 otherwise. So this is some 0, 1 real symmetric matrix. So every graph has a certain adjacency matrix, and the spectrum of this graph, so define the spectrum of G to be the spectrum of its adjacency matrix, that is the set of eigenvalues of A, or equivalently the roots of the characteristic polynomial chi A. So graph has a spectrum which is basically a collection of real numbers, and we will always arrange this in a certain form. So basic linear algebra says that the spectrum, because it's a real symmetric matrix, the spectrum is entirely real. Spectrum is real and will be arranged in the following way, in non-decreasing order: lambda naught, lambda 1, up through lambda n minus 1, where n is the number of vertices. I'll always use n to be the number of vertices of this graph. So the spectrum can be arranged in this form, and we are going to be interested in these eigenvalues of this graph. So let me repeat for emphasis: the polynomial chi A, the characteristic polynomial of a graph, is real rooted. All its roots are real. That's the same thing as saying that real symmetric matrix has, eigenvalues. That follows from the fact that a real symmetric matrix has real eigenvalues. I mention this specifically because real rooted polynomials and their generalizations play a major role in this theory of Ramanujan graphs. So I wrote down 3 graphs: the Peterson graph, the K5 and K33. So let's just look at their spectra. So for the Peterson graph, the spectrum consists of a 3 and 5 1s and 4 minus 2s. The spectrum of K5 has a 4 and 4 minus 1s. I am writing all this down because I want to just derive some, point out some features of this thing. The spectrum of K33 has a 3, 4 zeros, and a minus 3. Okay, so these are the spectra of the graphs that we have seen, and here is a very basic result of spectral graph theory. So proposition. It's a proposition in 2 parts. First, if G is D-regular, then lambda naught, the top eigenvalue, is D. And further, of multiplicity 1 if and only if G is connected. This is one result. And the second result concerns bipartite graphs. The last eigenvalue is always greater than or equal to minus D. So it starts with D and it can go at most up to minus D. So last eigenvalue is greater than or equal to minus D with equality if and only if G is a bipartite graph. In which case, something further nice thing happens, and this nice thing will be important for us later. In which case, the spectrum of G is symmetric about 0. So both these things can be observed from, for example, all of these. The Peterson graph is of degree 3, 3 is the highest value. K5 is of degree 4, 4 is the highest, it's 4 regular, and this is 3 regular. And of these, neither the Peterson graph nor the complete graph K5, neither are bipartite, but K33 is bipartite, and that shows that you see that in the spectrally you can see that -3 occurs in the spectrum, and this whole spectrum is symmetric around 0. So if you reflect it around 0, you get the same set back. So all of these things are illustrated by these 3 graphs, for instance. Now, we also need some definitions. So the values D and -D are called the trivial eigenvalues. -D when it occurs are called the trivial eigenvalues of G, and the rest are the non-trivial eigenvalues. And one more definition: the difference between the top and the next eigenvalues, that is lambda naught minus lambda 1, which is D minus lambda 1, is referred to as the spectral gap. Now, this strange looking thing is extremely important from the point of view of applications. So it is known that the spectral gap is a good measure of how well connected G is. So spectral gap, in some sense, measures connectivity of G. Not in a simple way, but in a way which is actually useful in various applications. So measures connectivity of G. So it is a good measure of the connectivity of G. And from the point of view of applications, it is desirable to construct graphs with large spectral gap. So we want to construct graphs with large spectral gap. Now, if I put it in the simple-minded fashion, then you could just take, for example, the complete graph on D vertices, or complete graph on D plus 1 vertices. There the spectral gap will be D, so you can make it as large as you want. But there is a problem with that graph, and the problem with that complete graph is the number of edges is quadratic in the number of vertices. We don't want, if you think of edges as laying wires, we do not want to be laying large amounts of wires. We would like it to be well connected, nevertheless have not many edges. And it is this spectral gap which somehow measures, which is a good measure, and we will try to see how to do this in a better way. Okay, so that brings me to the third part, which is expanders and Ramanujan graphs. So what are expanders? Expanders, basically, it's not a single graph. It's a sequence of graphs. So a sequence G1, G2, G3 of graphs is said to be a family of expanders. If the following happens, they should get larger and larger first. If the cardinality of the vertex set goes to infinity, and further, there should be a positive epsilon such that the spectral gaps of all of them, okay, so I should have said not just graphs, D-regular connected. So I'm only considering, we are only going to be considering D-regular graphs in this talk. So a sequence G1, G2, G3 of D-regular connected graphs is said to be a family of expanders if the vertex set cardinality goes to infinity, and further there's a positive epsilon such that the spectral gap d minus lambda 1 gn is always greater than or equal to epsilon. That is, the spectral gap is bounded away from 0. In this whole family, the spectral gap is bounded away from 0. So these are important from the point of view of applications. For example, if you have a good family of expanders, then you can design efficient algorithms for various problems. But what exactly is a good family of expanders? So this defines expander. What would be good? So since we said we want to make the spectral gap as large as possible, we would like to make the epsilon large. So want to make epsilon as large as possible. But there are limits. So there are results which say that you cannot make this too big depending on D. There are limits. So here is a theorem of Alon and Bopanna which says the following. So for a sequence of graphs as above, if you take the limit of lambda 1 gn, this number is greater than or equal to twice square root d minus 1. This is a result. Okay, this is proved by considering how many closed paths are there and doing some analysis with this thing. So this result of Alon and Bopanna says limit of the second eigenvalue is greater than or equal to 2d minus 1. So if you unravel this, what this says is equivalently, this says that the best possible epsilon you can have is d minus 2 root d minus 1. If you take anything larger than this epsilon, then you will not be able to find an infinite family of expanders for such epsilon. That's an equivalent way of stating this Alon-Bopanna bound. So this is supposed to motivate the definition of a Ramanujan graph. So a Ramanujan graph is the following. So it's d-regular connected, as always in this talk, d-regular connected graph, and every non-trivial eigenvalue, that is except d and minus d, every non-trivial eigenvalue is less than or equal to 2 root d minus 1 in modulus. So this is a bound not just on the second eigenvalue, but also on the last one, right? So last or second last, depending on whether it's a bipartite graph or non-bipartite graph. So bipartite graphs are somewhat simpler for reasons which we will explain soon. So with this definition of a Ramanujan graph, if you have a family, so a family G1, G2, G3 of Ramanujan graphs, all of that same degree, of same regularity D, therefore provide an optimal family of expanders. You cannot do better. So the question is now, do such exist? Can we actually find an infinite family of Ramanujan graphs, all of degree D, right? Now, the three examples that I gave, the Peterson graph, the complete graph, and the complete bipartite graph, all of these are Ramanujan graphs. If you look at the spectrum, I wrote down the spectrum for all of them. If you look at the spectrum, they all satisfy the condition that the non-trivial eigenvalues are at most 2 root d minus 1, where d is the regularity. So you do have plenty of Ramanujan graphs, but not all of same degree, right? Each one, all their degrees are kind of different. So the goal is to construct a large family, infinite family of Ramanujan graphs, all of degree, fixed degree. Okay, so why are these called Ramanujan graphs? So these were first defined by Lubotsky, Phillips, and Sarnak. And they gave examples of Ramanujan graphs. So they gave examples of Ramanujan graphs. So constructed Ramanujan graphs as the Cayley graphs of PSL 2Z mod QZ or PGL 2Z mod QZ with respect to P plus 1 generators, where P and Q is a prime much larger than P, where P and Q are primes. And these P plus 1 generators are related to expressing P as a sum of 4 squares. The construction, okay, so the description of these graphs is easy, right? We can explicitly say what the generators are and what the groups are, and so the Cayley graph can be easily constructed. But the proof that they are Ramanujan graphs is not at all easy. So it uses this conjecture, Ramanujan conjecture, which was proved by Eichler and then in lots of cases, and later by Igusa in the remaining cases. So they actually use Igusa's results on the Ramanujan conjecture to show that these graphs are Ramanujan graphs. So this is some high-powered number theory. Another construction was also known due to Margulis, and that also is quite high-powered number theory / algebraic geometry, or both together. In all cases, until this paper of Marcus, Spielmann and Srivastava, in all cases, whatever Ramanujan graphs were constructed had regularity a prime power p to the n plus 1, where p is a prime. Because all these construction depended on finite fields which have order p to the n, and all of these had only regularity p to the n plus 1. So it was not known, for example, if you take something like 7, can you do it for 7? Is there an infinite family of 7 regular Ramanujan graphs? This question was not known until this paper of Marcus, Spielmann and Srivastava. To the next part. So let me deal with something called two lifts. So what is a two lift of a graph? So G equal to VE is a graph. So the graph G hat with vertices V hat, E hat is a two lift of G if the following happens. Two conditions should be satisfied. So first, for each vertex V of G, there are two vertices, V0 and V1 in V hat. And for each edge VW of G, there are two edges in V hat, and further, which are either one of two types, which are either the pair V0 W0 V0 W V1 W1, or the pair V0 W1 V1 W0. So we will call this uncrossed edge and call this crossed edge. So let me just draw a picture for this. So here is V and here's W, and above V there are two vertices, V0 and V1, and above W there are two vertices, W0 and W1. And for this edge VW, there are two possibilities. Either I can do it uncrossed, which I'll draw in blue, or I can draw it crossed. I can draw this. So a graph which satisfies these conditions is called a two-lift. So if I were to use in the language of topology, so a two-lift is a two-fold covering space of G. And two lifts preserve properties that we are interested in. So the properties that we are interested in are, first of all, we are interested in regularity. So two lifts preserve deregularity. If the base is deregular, so is the top space. And that's because it's a local homeomorphism around a vertex V at the bottom and around the vertex V0 and V1 on top, everything looks the same. So two lifts preserve deregularity. And second, two lifts preserve bipartiteness, the bipartite property. So these two properties which we are interested in are preserved by two lifting. So here is a picture which shows you three different two lifts of the triangle graph. So let me flash one picture. So these are three different lifts of the complete graph on three vertices, which is the triangle graph. So you can see that in the first one, these blue edges represent the uncrossed and the red ones represent the crossed. So in this, one of the edges is uncrossed. So this edge is uncrossed, while these two are crossed on top. Here all edges are uncrossed, and here all edges are crossed. All are red. So the case when all edges are uncrossed will just give you two copies of the original graph. While the case where all edges are uncrossed gives you the so-called double cover of that graph. So the double cover of this triangle graph is this hexagon. If you look at this, although it looks all horribly convoluted, if you unravel it, it's just a hexagon. So these are examples of two lifts of the triangle graph. So two lifts, as you can see from this picture, you can associate them. How many two lifts are there? So how many two lifts? Of G. So if the cardinality of E is M, then clearly there are 2 power M two lifts. Each edge you can either lift it in crossed fashion or uncrossed fashion. As you please, there's no restriction at all. Whatever graph you get, that's a two lift. And so since there are M edges, there are 2 power M two lifts. And these are associated to signings of G, what they call signings of G. Associated to signings of G. So a signing of G is just a function S from the edges to plus minus 1, as I've shown in these examples. So when this thing is 1, then you lift it blue. When this thing is minus 1, then you lift it as red, right? So there are 2 power M two lifts associated to the 2 power M functions from E into plus minus 1. So here is a very simple-minded idea to construct Ramanujan graphs. So idea is the following. So take a graph, take a Ramanujan graph to begin with. Consider a two lift and hope that for some proper signing, for some signing, it still remains a Ramanujan graph. As I said, it has the same degree. The degrees of the vertices, the same regularity. If you two lift a graph, it's still deregular graph lifts to a deregular graph. So you'll get a Ramanujan graph with a larger number of vertices and then iterate this construction. So this is a simple-minded idea. So in order to actually go through with this idea, one needs to understand what is this Ramanujan graph notion is spectral in nature. So one needs to understand the spectrum of a two lift. So the spectrum of a two-lift G hat. So this was done by Bilu and Lineal in 2006, and this part is not very difficult. This particular statement from their paper is easy to prove, and what they show is the following. So let S be a signing of G, and consider the signed adjacency matrix. A sub S, defined by, it's similar to the adjacency matrix. A sub S of VW is S of the edge VW if it's an edge, and 0 else. It's very close to the adjacency matrix. In an adjacency matrix, we always had 1. Here it is 1 if S of that edge is 1, -1 if S of that edge is -1, and 0 of that pair doesn't form an edge. So this also is a square matrix, just like the adjacency matrix, same size adjacency matrix. Also a real symmetric matrix with 0 and ±1 entries. So real symmetric with 0 ±1 entries. Okay, so what they show is that the spectrum of the lift sigma of A hat is the original spectrum plus new eigenvalues and union, right? They all come from AS. So the union of the spectra of A and AS is the spectrum of A hat. This is reasonably easy to prove. And then they made a conjecture. They conjectured that for some S, for some signing, sigma of AS is contained in -2 root D minus 1 to 2 root D minus 1. Of course, if this conjecture were right, then some lift of a Ramanujan graph would also be a Ramanujan graph, because the new eigenvalues are all in the range that we want. They, in modulus, they are less than 2 root D minus 1, and already the old ones were known to be in modulus less than 2 root D minus 1, except the trivial ones. And so that means every eigenvalue of A hat, non-trivial eigenvalue of A hat, would be in the required range. And so you from a Ramanujan graph with n vertices, you will get a Ramanujan graph with 2n vertices and iterate the procedure to get an infinite series. So this was the conjecture made in 2006. So Marker, Spielman and Srivastava proved this for, not in general, but they proved this for bipartite graphs using a very ingenious argument based on the probabilistic method. So let me now get to how this probabilistic method enters into this. So this is section 5. The matching polynomial of a graph. So the matching polynomial is, so first of all, what's a matching? So a matching in G is a subset of the edge set, all of whose endpoints are distinct. And let M sub I denote the number of matchings with I edges. So the matching polynomial of D is a certain polynomial defined as follows. Mu G of X is the summation over all I minus 1 to the I mi x to the n minus 2i. So this is the matching polynomial of G. So as you can see, what's the top term? So minus 1 power 0, m0 x to the power n. m0 is number of matchings with 0 edges. That's because there's just one matching, the empty set. So the matching polynomial is degree n monic polynomial. just like the characteristic polynomial. This is also a degree n monic polynomial associated to that graph. Now, in 1972, Heilman and Lieb proved the following about the matching polynomial. They proved that mu g of x is real rooted first. All roots of this matching polynomial are real. So mu g of x is real rooted, and further every root of this is less than or equal to 2 root d minus 1 in absolute value. So if you see, here is another context in which this number 2 root d minus 1 is occurring. One we already saw in the Bopanna-Alon result, that there was a 2 root d minus 1, and here is another context which arises from some combinatorial thing about the graph. Again, this 2 root d minus 1 is occurring. So there is some reason for this. So we'll get to this later. Okay. So, and how do they prove this? This proof is not very difficult. So let me skip over this. Let me skip the proof of this one. But what is the relation of the matching polynomial to two lifts? So that seems to be one thing we did, and this seems to be another thing. What exactly is the relationship? So what is true is the following. Gottsel and Gutman in 1978 proved that the matching polynomial of G is the average over all signings. There are 2 power m signings, as we said. Average over all signings of the characteristic polynomial of the signed adjacency matrix. So this is what they proved. And this proof is a very pleasant and nice proof. And Marcus, Spielman, Srivastava give another version of this proof as in an appendix to their paper. So how does this help? How does this help us do what we want? It does not. On the face of it, it really does not help. So where are we? So we are starting with a Ramanujan graph of degree d and trying to show that some 2 lift is Ramanujan. We know that the spectrum of the 2 lift is the original spectrum plus the spectrum of the AS, the signed adjacency matrix. So it is enough to show that some AS has spectrum in minus 2 root d minus 1 to plus 2 root d minus 1. We want to show that one of the terms, one of these polynomials has roots in minus 2 root d minus 1 to 2 root d minus 1. But that we don't know. What we know is the average of all of these satisfies that property. We know that mu g of x has the property that its roots are between minus 2 root d minus 1 and 2 root d minus 1. But what exactly does the roots of a polynomial of various polynomials have to do with the roots of their average? So not really that much, right? So if you think about it, in general, the sum of polynomials, the roots of a sum of polynomials, they bear no particular relationship to individual polynomials. So what Marcus, Spielman, and Srivastava do is they determine a very interesting condition on these polynomials from which you can go to the average to the roots of mu g x to the roots of at least one of these. And that is the concept of interlacing. So that brings me to the next topic. So which one was it? 5, 6. Interlacing is a very classically known thing. So let's make a definition. So let f and g be polynomials, one variable polynomials of degrees n and n minus 1 with positive leading coefficients. Always we will have positive leading coefficients in the rest of the thing whenever we talk about interlacing. So f and g are polynomials with positive real coefficients and they are real rooted. Suppose that the roots of f are beta 1, beta 2 up to beta n, in increasing order. And the roots of G are alpha 1, alpha 2, up to alpha n minus 1, again in increasing order. So we say that G interlaces F if it goes this way. So alpha 1 lies between beta 1 and beta 2, alpha 2 lies between beta 2 and beta 3, alpha n minus 1 lies between beta n minus 1 and beta n. So this is the basic definition, and as I said, this is very classical 18th century. There's a Cauchy interlacing theorem, for example. Okay, so there are many equivalent conditions for interlacing. So the following are equivalent. 1, G interlaces F. Second, that G by F has a certain partial fraction expansion, which looks like this, is the summation I equals 1 to k of Ci by x minus gamma I, where the Ci's are all positive. It has a partial fraction expansion where the numerators are positive real numbers, denominators are linear polynomials in x minus gamma I. And the third condition, which doesn't seem quite related to this, is that F plus lambda G is real rooted for all lambda n r. So all these conditions are equivalent to G interlacing F. Now, it's not enough to have just one polynomial. We also need a family of polynomials. So if we have polynomials f1 up to fk, so f1 up to fk are said to have a common interlacing. If equivalently, two conditions. One, there exists a G, all of same degree, right? All of degree n, and positive leading coefficient. If there exists a G of degree n minus 1, interlacing everything, each fi, or, and this part's not very trivial, that every positive linear combination of f1 up to f1 up to fk is real rooted. So interlacing is linked up with real rootedness. So what Spielman, Srivastava and Marcus do is they prove a very simple but extraordinarily useful observation. So let me write down that observation. The observation is the following: is that if f1 up to fk have a common interlacing, and Fe denotes their sum, then there is some I for which the maximum root of Fi is at most the maximum root of Fe. And this is exactly what we will need. So let me just go back a little bit. So if you see, we wanted to bound the roots of one of these. We have a bound on the roots of this, which is their sum. It's their average, but it doesn't matter. It has the same roots as their sum. So we have a bound on the roots of mu g, and we wanted to bound the roots of determinant of the characteristic polynomial of the AS. And if you knew that these somehow had a common interlacing, then we would be done. we would be done with almost everything, right? So it remains to see. It remains only to see. Yes.
I just hate to interrupt, but there is slightly less than 5 minutes left.
Yes, thank you. Thank you. Yes. So it remains only to see the following. So it remains to see that the polynomials chi-as of x do have a common interlacing. And this is what they do in the last and most technical section of their paper. So what does the proof use? So the proof uses various things. So the first thing the proof uses is something called real stability. Real stability is a multivariable generalization of real rootedness. It uses this. Then second thing is it uses differential operates. So this is the work of Borsia and Brendan. And then it uses very classical algebraic identities such as the matrix determinant identity. All of these are used in a very beautiful fashion. So that paper is a real pleasure to read. So using all this, they show this interlacing property and thereby establish the existence of Ramanujan graphs of all degrees, except that they do it in the bipartite case. So let me just remark why only the bipartite case. Only the bipartite case because in all of these things, they are only bounding the largest root. So there is nothing known about on the other end, the smallest one, whereas the definition of Ramanujan graph, you need bounds on the largest as well as the smallest, the second largest as well as the smallest. So, but if it's a bipartite graph, the symmetry around the origin will be enough to do it for the largest, second largest root. And that is why they restrict in this paper to bipartite graphs. Okay, so I'm more or less done. I just want to make one remark. Okay, so the same techniques, they use the same techniques to prove a famous conjecture in operator theory known as the Cadison-Singer problem. So they settled this affirmatively. It was long thought that this is false, but they use the same techniques of interlacing to settle the Cadison-Singer problem. So this is to indicate that this method of interlacing is not just a one-shot thing. So I think it bears further study. So I think I'll stop here. Thank you very much.
Thank you so much for this wonderful talk. So I think it is a tradition, somewhat unfortunate in after award lectures, but I just use that fact to give you all the time, and I wish you could go on.
Thank you.
So of course, if it were a physical meeting, I would have handed over to you some certificate, but I would just ask the organizer to display it.
Yes, sir. Sir, you are requested to offer a certificate.
Yes, so I offer you a certificate, Vijay.
Okay. Thank you very much.
Yeah, there you are.
Thanks.
Thank you for this wonderful talk. You probably mentioned, I think this work of Nikhil Srivastava and Marcus Spillman was in the news recently because he got the inaugural Foyas Prize of the American
They have
Math
got
Society.
several prizes, at least 3 or 4 awards for this.
Polya Prize earlier and the Head Prize and so on. But
Yes.
this is apparently very recent, and it's given to him on 5th January at the joint meeting. But nice to your talk to get to know something about the work and so on. So thank you once again, and
Thanks a lot.
I guess we move to the next session.
Thank you, Professor Vijay Kodiyalam, sir. I
Thank you.
feel I'm not attending the lecture online. I feel I'm attending the lecture offline in the class. In such a way, you have explained the mathematics in simple language. Thank you very much, sir. I would like to express my sincere thanks to chairperson of this session, Professor Sudhir R. Ghorpade, sir, and all the attendees. Thank you very much. Next session will start very soon in the same link. And let me tell you, all of you have, for all of you, we have organized cultural program at 7 p.m. That is a Sparkle poetry program composed by our students. So I request all of you to attend that program.
No question
Now,
hours, no
I
query.
hand over this session to Professor Dr. Kranti Zakade, madam. Thank you.
Thank you, sir.
I'm sure people have questions. They can write to Vijay.
Professor Barua, sir. Sir, should we start
Hello?
next session?
Yeah.
Should we continue
Am I
next
audible?
session?
Am I
Yes, sir,
audible?
yes. You're audible, sir.
Oh.
You're audible.
Okay. Thank you. Thank you so much.
So, on behalf of Indian Mathematical Society and MGM University, I, Dr. Kranti Zakade, welcome you all in this session, that is lecture talk by A.K. Agarwal Award winner by Dr. Arjun Pal, Jadavpur University, Kolkata. Now I request Professor N.D. Barua, sir, to chair this session. Over to you, sir.
Thank you so much. So I hope the speaker is online. Yeah.
Yes.
Yes, I'm online.
Good morning, Dr. Pal. The speaker for this session is Arjun Pal of Jadavpur University. So this year he has been awarded the Professor A.K. Agarwal Paper Award. So he is from Jadavpur University, Kolkata, and Dr. Pal will be speaking on fundamental group schemes of Hilbert scheme of endpoints. So I now it's over to Dr. Pal, please.
Okay, thank you. So let me first share my screen. Is it visible?
Yeah.
Okay. So first of all, good morning everyone, and let me first thank the organizer. And first of all, myself and Ronnie Sebastian would like to sincerely thank the Indian Mathematical Society for appreciating our work with the A.K. Agarwal Award 2021. I would like to thank the organizers of the 87th annual conference of the Indian Mathematical Society for giving me an opportunity to give a talk in this conference in connection with this award. So let me begin. So the title of my talk is Fundamental Group Schemes of Hilbert Scheme of Endpoints on a Smooth Poetic Surface. So this is a joint work with Professor Ronnie Sebastian. So let me begin. So first of all, I will briefly mention about topological fundamental group and especially two types of fundamental analog of fundamental groups that appears in algebraic geometry, namely Norris fundamental group scheme and S fundamental group scheme. And then finally, I will talk about our joint work on computation of fundamental group schemes of Hilbert scheme of endpoints on a smooth poetic surface. Okay, so we know that topological fundamental group of a space together with some mark points is called base point. This is basically a group of homotopy classes of loops inside X based at a given point X naught. So this notion of homotopy class of loops, this works well for topological space mostly that are Euclidean like manifolds and so on. But in algebraic geometry, the spaces we are interested in, their topology are mainly Zariski topology, which is quite different from the usual manifold topology or Euclidean topology. This is the main reason that usual notion of homotopy class of loops cannot be generalized in a straightforward way in case of algebraic geometry, in case of algebraic varieties or schemes. So, for example, if we take the generalization of this notion of fundamental group in a straightforward way, most of the nice schemes of the algebraic variety, which are mainly integral schemes, they become contractible. So, and their fundamental group become trivial. So, therefore, this notion straightforward generalization is not good. So, therefore, there is another way to generalize this notion. Namely, we know that for nice topological space, we can view topological fundamental group as an automorphism of its universal cover when universal cover exists, right? So this way of this different approach is good to generalize this notion to the case of algebraic varieties. Okay, so following this idea, in SGA1, Alexander Grothendieck first introduced the notion of Ithal fundamental group of a variety, or more generally for schemes together with some geometric point. This is some analog of topological fundamental group, and this notion is basically what he has taken, that instead of looking at universal cover, so we know that in algebraic geometry most natural analog for a covering is basically finite Ithal covers. Okay, and because of finiteness, universal cover cannot exist in the category of all finite Ithal covers. But therefore, so that's why we have to take all kind of Ithal covers, finite Ithal covers, and look at the fiber of a given Ithal cover, fiber of over the given base point. Okay, and look at the automorphism of the fibers. So this is a natural way to generalize the notion of a fundamental group in algebraic geometry, and this automorphism is basically called Ithal fundamental group of that variety. This notion works quite well. For example, if we consider only smooth projective variety defined over complex numbers, then it turns out that this variety has an underlying complex manifold structure. Means if we look at the complex valued point of the variety, this has a structure of a smooth manifold. So now once we get a smooth manifold, we can talk about its topological fundamental group, right? So the relation between Ithal fundamental group and topological fundamental group is that if we look at the topological fundamental group and look at the profinite completion, then this profinite completion, which is denoted by pi1 topological x and hat, this is isomorphic to Ithal fundamental group. Okay, so therefore this notion of Ithal fundamental group for algebraic variety is quite well, but that is a serious problem if we consider the variety defined over positive characteristic. Okay, because the notion of Ithal fundamental groups involves the Ithal covers only, and the Ithal covers means they are on basically separable covers, and which are unramified. Okay, so that's why in positive characteristic, this kind of covers misses important geometric information coming from inseparable covers. So to remedy this situation, Madhav Nodi in 1976 he has introduced the notion of a fundamental group scheme by replacing the Ithal covers, finite Ithal covers, by more general kind of covers, which are basically essentially finite vector bundles over X. Okay, and he has shown that if we consider the category of all essentially finite vector bundles, and if we fix a base point, say x0 in the variety X, then if we look at the fiber of each of the essentially finite vector bundle over the given base point, which is basically a k vector space, and then we get a functor Tx0, which sends a essentially finite vector bundle to the fiber of that vector bundle at the given point x0. Okay, then if we consider the automorphism of this functor, so then this is representable by a affine group scheme. This is basically by a general theory of Tanaka category. So this group scheme is known as the Nodi's fundamental group scheme, because Nodi first introduced this group scheme and studied this group scheme. This is denoted by pi1 n x comma x0. So this is a one type of analog of fundamental group in case of algebraic variety. Okay. So later Nodi extended this notion for arbitrary schemes which are not necessarily proper, but they are reduced and connected, geometrically connected and finite time by looking at all G torsors, means by looking at the category of principal bundles defined over X. Okay. And it turns out that if we look at the all finite dimensional representation of these fundamental group schemes, then this category is essentially equivalent to the category of essentially finite vector bundles, which we have started with. Okay. Now later, this notion of fundamental group, which is basically a group scheme. Group schemes means group together with a scheme structure. This notion was generalized later by A.K. Parameshwaran, by Indranil বিশ্বাস, A.K. Parameshwaran, A.J. Parameshwaran and S. Subramaniam. They basically wanted to study the notion of monotony of principal bundles. For that, they have introduced a notion of fundamental group scheme, which is kind of analog of Norris fundamental group scheme, by looking at the category of all numerically flat vector bundles, which is more general kind of covers than the category of than the essentially finite vector bundles, which Nodi considered. So they have shown that if we look at the category of all numerical flat vector bundles over a smooth poetic curve C, and look at the Pfeiffer functor by attaching every essentially numerically flat vector bundles to its Pfeiffer over a given point x0, then this forms a neutral Tanakian category. So therefore, by taking the Tanakian dual, means the automorphism group of the Pfeiffer functor, we get a fundamental group scheme, which is known as S fundamental group scheme. Okay. So they have done it for the curve only, means smooth poetic curve defined over algebraic closed field. But later in 2011, this notion was generalized for higher dimensional connected proper K varieties independently by Vikram Mehta and Adrian Langer. But Mehta did not publish his manuscript, but Langer has published and studied that group schemes in more detail. Okay, for higher dimensional varieties. Now, in this case also, we get a if we look at the finite dimensional K-linear representation of that group schemes, this category of representations becomes equivalent to the category of numerically flat bundles defined over the variety X. Okay, and this equivalence is not only just equivalence, this equivalence preserves K-linear structure of that category, and not only that, it preserves tensor structure. Okay. Now, in general, till now we have mentioned three kind of analog of fundamental groups in algebraic geometry, namely Ethel fundamental group, Norris fundamental group scheme, and S fundamental group scheme. These three groups are nicely related by the following relation, that there are faithfully flat group homomorphism of group schemes from pi1 S x comma x0 to pi1 n x comma x0 to pi1 Ethel of x comma x0. Okay. In general, this Norris fundamental group schemes, this carries more information, more geometric information of the variety than the Ethel fundamental groups, and the S fundamental group scheme carries more geometric information than the Norris fundamental group scheme. Okay. If we consider the variety defined over only characteristic algebraic closed field of characteristic 0, then it turns out that this Norris fundamental group scheme is isomorphic to Ethel fundamental group scheme. But in positive characteristics, they are actually different. Okay. In positive characteristics, this fundamental group scheme carries more geometric information, carries from the coming from the inseparable covers. Okay. And in general, even if we take X to be a curve, smooth poetic curve, this pi1 S, that means S fundamental group scheme of that curve is much larger than pi1 N for curve. Means most of the curves, because there are on smooth poetic curve there can be some kind of numerically flat line bundles which are not necessarily torsion. So this is one of the reasons why in general pi1 S is much larger than pi1 N. Okay. So let me come to the come to our joint work on computation of fundamental group schemes of Hilbert scheme of endpoints. So this is joint work with Ronnie Sebastian. So let me begin with what is called Hilbert scheme of endpoints on X. So this is quite classical and very well studied in the literature. So suppose in our setup we fix an algebraic closed field K of positive characteristic. Okay. So though Hilbert scheme is defined for any schemes regardless of characteristic of the base field. But for our work we will only focus on positive characteristic. Okay. So now we take X to be a irreducible smooth positive K variety of dimension 1 or 2. That means X is either curve or for dimension 2 means it is surface. Okay. Now we fix an integer, positive integer n greater than or equal to 2, and let Hill when X be the Hilbert scheme parameterizing effective zero cycles of length n. So basically, very roughly speaking, this is kind of zero cycles means zero dimensional closed subschemes. That means this is basically a bunch of points in the surface or in curve, and the point is that we can repeat, we can take a point repeatedly. Okay. So a typical point, let me go to the next slide so that, so a typical point is basically some kind of a positive integer times some point while X is some closed points and take the formal sum. This kind of, so this is a very rough description of points of Hilbert scheme. Okay. So they are basically zero cycles. So Hilbert scheme, Hill by X, this is a smooth positive K variety of dimension ND. So that means for when X is curved, this is a n-dimensional variety, and for surface, this is a 2n-dimensional smooth positive variety. Okay. And Hilbert scheme is very important kind of example of moduli space, and this is studied by many authors from various point of topological and also algebraic point of views in literature. For example, one can get a nice survey on study of this Hilbert scheme in the HGA explained. Okay. So it is a natural interesting question whether we can compute the fundamental group schemes for this Hilbert scheme, and we can talk, relate whether we can give a relationship between the fundamental group scheme of Hilbert scheme with that of X. Okay. So for this, so let me introduce a notion that let Snx be the n-fold symmetric product of X. So this is basically you take x to the power n. X to the power n means product of X with itself n copies. So x cross dot x n copies, and on these n copies, this product, there is a natural action of the symmetric group Sn by permuting its factor, right? So if you look at the quotient, then this quotient is a normal projective variety. Okay, that normal projective variety is denoted by Snx. This is called n-fold symmetric product of that variety. So this is a normal projective variety of dimension ND, and when X is a smooth projective curve, it turns out that Snx is naturally isomorphic to Hilbert scheme, but for surface, when X is a smooth projective surface, Snx is not isomorphic to Hilbert scheme, but rather that Hilbert scheme can be seen as a natural dissimilarization of Snx. Okay. So we fix, so as before, we fix a smooth projective surface, irreducible smooth projective surface defined over as a very closed field K, and there is a natural map which is called Hilbert-Chow morphism from the Hilbert scheme of endpoints on X to the symmetric product Snx. This is known as Hilbert-Chow morphism, which basically takes a typical point of Hilbert scheme, that is basically zero cycle of length n, and send it to the formal sum given as follow. You take the point and take multiplicity to the length of the local ring of that that zero cycle at the point x. X is supporting the x is inside the support of that cycle. Okay. So this is very rough or say theoretical description of the this morphism. Okay. It is known that this morphism phi is actually a proper morphism. In fact, this is a projective morphism. Now we fix a point, close point, say x naught inside X, and we take nx tilde to be the point of a point of Hilbert scheme, which goes to nx naught in the symmetric product Snx by this Hilbert morphism. Okay. So nx naught means that x naught plus x naught dot dot n times. So okay. So the same point we are taking n times. So this is the point in Snx. So now one more notation that for any affine K group scheme G, we do not buy G suffix AB to be the abelianization of this group scheme. So this is basically the largest affine quotient group scheme which is abelian. Okay. So now let me state the main result of our joint work with Rory Sebastian. So we for some technical reason we have to assume that characteristic of the base field is strictly greater than 3. Okay. Now X is a irreducible smooth poetic surface defined over that algebraic closed field K. Then there is a natural isomorphism of affine K group schemes from pi 1 x comma x naught abelianization to pi 1 Hilbert scheme of endpoints on the surface X with base point nx tilde. So here I have used this sign this is basically shorthand, means this isomorphism is valid for each of the cases. If you look at the S fundamental group scheme, and if you look at the Norris fundamental group scheme, and if we consider the Ethel fundamental group also. Okay. So basically first we have proved this isomorphism for the S fundamental group scheme, then we have derived it for Norris fundamental group scheme, and finally we have concluded that for the same isomorphism for the Ethel fundamental group scheme, that case. So in particular this isomorphism shows that pi 1 this each of these fundamental group scheme of the Hilbert scheme is basically abelian, because this is isomorphic to abelianization of certain fundamental group schemes. Okay. So in another joint work with Ronnie Sebastian, so we have proved the similar kind of isomorphisms for X is a smooth poetic curve, means dimension 1 case. And in that setup, we don't need the assumption that characteristic of the base field should be strictly greater than 3. We have proved that same isomorphism for the case of curve for any positive characteristic. Okay. So let me let me tell you that this isomorphism for the case of Ethel fundamental groups was known by work of Indranil Vishwas and Amit Hogadi by their 2015 paper. So, but their approach is different from our approach. So, yeah. So now in the next slides, let me very briefly give an outline of the strategy of our proof. So basically, so a typical point of Snx means the n-fold symmetric product of that variety. This is basically formal sum of closed points, say R1 x1 plus Rp xp. By Ri, they are basically positive non-negative integers, and x1, x2, xp, they are basically distinct points, and we can write it in a consistent way, so that by specifying that R1 greater than equal to greater than Rp. Okay, and we have to impose the condition that the sum of these multiplicities, that is sum of Ri, is equal to n. Okay, so this ordered tuple R1, R2, Rp is known as the type of that point. So if we look at the points of the Snx, if we look at the open subscheme in Snx consisting of the points of type x111, that means all the multiplicity 1, and of the type 2, 1, 1, that means exactly 2 points are repeating and all the points are distinct, then this forms an open subscheme inside Snx. And if we look at the inverse image of that open subscheme, say this V, this is an open subscheme of the Hilbert scheme. So basically now we have another morphism from x to the power n to Snx. This is basically quotient map by the action of symmetric group. So now we considered a numerical flat vector bundles over Hilbert scheme restricted to a vector bundle restricted to V to get a vector bundle, push it forward, and then pull it back by this morphism psi, restriction of this psi. So we get a shift on this open subscheme of x to the power n, and then take the push forward and take double dual. So this is kind of way to go from Hilbert scheme, to go from bundle defined over Hilbert scheme to the bundle defined over x to the power n. So this is our main strategy. Any question?
It's okay. Hello.
Yes.
You can carry on.
Okay. Okay. So
Kindly mute the participants. Kindly mute your mics. Yeah, Dr. Paul, please carry on. You have, I think, 5 minutes more.
yes, I'll be finishing soon. So this is a way to go from the numerical flat vector bundles to numerical flat vector bundles defined over x to the power n. So now we have shown that this functor is basically very nice, namely that this functor is basically preserved direct sum, K-linear structure, and tensor product, and all these nice properties are satisfied, so that we get a homomorphism of fundamental group schemes from pi 1 s of x to the power n to pi 1 s of Hilbert scheme. So now then there is a by a result of Langer, this product of fundamental group scheme of this product variety x to the power n is naturally isomorphic to the product of fundamental group scheme of each of these copies. Okay, and this resulting morphism, we have shown that this resulting morphism, this composite map, is actually Sn invariant. Therefore, from this fact, we have deduced that that this homomorphism induces a homomorphism of pi 1 x comma x naught abelianization of these group schemes to the Hilbert scheme. So this is our required homomorphism of fundamental group schemes. Then we have used a result of Delin and Milne to check that this homomorphism of group scheme is actually a closed immersion and faithful flat, and hence this is an isomorphism of affine group schemes. So this is our strategy of these things. So yeah, that's all. So here is some references. Yeah, that's all I plan to say.
Okay, thank you so much, Dr. Paul, for your nice talk, and congratulations for your nice work also. And as in the tradition of the IMS annual meeting, so I think that questions are not allowed to ask by the participants. But if they have any questions, then I hope that they will forward it to your email. So
Sure.
and you'll be able to.
Sure.
Okay. And if there is any certificate from the organizers, Professor Orule, I kindly request you to please show it, and yeah, so it's a big appreciation for Dr. Paul. Thank you so much again.
Okay, thank you everyone for patience. Okay, thank you. Thank you very much.
Professor Orule, your mic is, I think, muted.
Yes. Congratulations, Professor Paul, sir. And I thank on behalf of IMS and MGM University for such a nice lecture talk. And I thank Professor Barua, sir, for chairing this session. Thank you very much, sir. So there is one request to all.
Hello. Hello, Professor Orule.
No voice.
Okay.
Am I audible, sir?
Yes. Yeah. Now.
Now, please go ahead. Yeah. Again, no voice.
Students from Jawaharlal Nehru Engineering College, MGM University has arranged a small cultural
Hello.
Little hiccup sometimes.
So all are requested to attend evening session, Sparkle. Now this
Okay, so I now just switch over to the organizers for the next session. Thank you so
The
much.
next session will be at 10:40, which will be the parallel session, the invited talk 1 and invited talk 2. The separate links has been provided to view already. Please join the session.
Okay, thank you so much for all the participants, and now I think we can move on.
thank you.